here it would be 12 and here it would be 11. Likewise, if I make 12 as a root, then it would be 10 and it would be 11. And we have one more combination of this tree as well. So that would look it could be like if I keep if here I have so I think 1, 2 and 3, like can we have any other node structure? So if I store 11 here, then I think this would be another 10. Likewise, I think we can have one such here as well. So I want to first explore all possible binary search trees. Then we will begin the approach so that we will understand what exactly we are trying to do. If it is this, I think here we will have 11. No, here this is what we can have. This would be 11 and this would be 12. Okay, so any other combination of BSTs? So given a tree, how many BSTs we would be having? I think it has a formula. What is that form? Can you guess that formula? I think you might have seen that in data structure. So there is a standard formula to determine uh, how many binary search trees we have. So there is a formula, something we use Catalan, and there is a formula, and accordingly, then we find the number of BSTs. I think for this 3 node and 3 frequency node, these are the possible BSTs. So given this nodes and frequencies, can you compute the cost of this each node? So what I will do is I'll show you how to compute cost for this node. You can repeat it. So every student can take one, and we can just finish it. So let us say I want to find out the cost of this node. What I do, if I want to compute the cost of this node, what I do, how is the cost computed? See, when I said we are computing the cost of BST, the cost is nothing but total number of memory read operations required as per the given frequency of each node. So now what I say is that I have 10 here and say 10 will be read twice. In order to read 10, you need to read 11 and then you need to read 10. So for that we had found that the cost of total BST can be computed as the frequency multiplied by level. If you do it for each node level wise for the tree, and if you take a sum of that, it gives you the total cost of the optimal binary search tree. So for this tree, the currently the balanced one, 10, 11 and 12, the cost would be, so frequency of 11, what is the first node is 11, this is at level 1, this is at level 2. So frequency of 11 is 1 into level plus how many nodes I have below level 2. So the frequency of node 2 is 2 multiplied by level plus the frequency of node 12, what it is, 6 multiplied by 2. So if you take sum of this, it gives the total cost of that tree. So what's the sum? 1 plus 4 plus 12. So it is, am I right here? Okay, 4, 16. Okay, so this cost of this tree is 17. So likewise, what I want you to compute this cost for this tree, cost for this tree, cost for this tree, and cost for this. Then the minimum of this gives me optimal binary search tree. But this is called a brute force approach. We are trying out for all the combinations and we are computing the cost. So we will first find out what is the minimum, because we need to know that whether our approach is giving right answer or not. So that's why better we first compute this cost for that. So can you give me the cost for this tree? We'll go cycle wise. Okay, I've computed this. I want cost for this. Can you just give me the cost for this? So what it is? 10. 10 means frequency of 10 is 2. 2 into the level at which the node 10 is 1, plus the frequency of node 11 is 1, multiplied by the level at which that node is there, which is 2, plus the frequency of node 12 multiplied by the level at which the node is situated. So what's the cost? 2 into 1, 2 plus 2 plus 18. So it is 22. Right. Can you compute for this? Okay, so 1, 2. I want cost for this node. 14. Okay. Is it 14? Okay. I'll just go on. Cost for this would be 14. And the cost for this highlighted ones, 13. And this one, final ones, is 17. I think it's a 17. Okay, so which is minimum? Which is minimum? Which is minimum cost here? This looks as the minimum one. Fine. So 13, this tree is the minimum one. I mean, you need to arrange this three nodes with given frequency in this BST format. I mean, we need to make 12 as a root, then make, considering 12 as a root, insert the nodes. That's how we need to do it. And when I say 12 as a root, you need to make left as 10 and then you make 11 as a child of 10. That's how you need to construct this binary search tree. But the approach which we are looking at, this is called as brute force. So for 3 nodes, we are going for 5. But if it is 4 nodes, we will suddenly we'll have to compare for 18 or 20, more than 20 plus combinations. If it is 5, it's almost 60 or 90 or something. So it exponentially grows. And I cannot rely on generating all combinations of binary search tree and then computing cost and from that obtaining minimum. So that's a brute force approach, and it will give you a solution, but it's not an approach to be adopted, because soon you will hit a limit, and that's of it usually goes into exponential complexity. And as you all know that we never use algorithm with exponential complexity unless we do not have an option. But this can be constructed far more easily by using a dynamic programming approach. So let us see that dynamic programming approach. Fine. So I hope you understood why it is 13 and why it is minimum. So what we found that this tree, this node, the least cost is 13. So what I'll do is I'll retain that and rest all I'll delete. Okay. So this one I'll retain here just for a sample once. Okay. So now, okay. So now let us solve this program by something called as dynamic programming approach. Now, when I say dynamic programming approach, basically what we do is we start with the smallest subproblem of this. We give a solution to the smaller subproblem, and what we do is we start building solution based on this subproblem. And during the process of building solution to the subproblem, what we do is we try to build solution to a larger subproblem based on solution of smaller subproblems. So that's how we keep on merging the solutions of subproblems till we reach solution to my original problem. That's a dynamic programming approach. And during this process, if I have solved one subproblem, and if their need arises to solve same sub problem again, we do not solve that again. What we do, every time we encounter a sub problem which we need to solve, if that sub problem is already solved, we will never resolve it. What we do, we keep storing the solutions of sub problems in some another data structure, and whenever a need arises to get a solution for that sub problem, instead of resolving it again and again, we just pick up the solution which we already computed and stored in some additional data structure. And in most cases, this additional data structure is a table. It could be two-dimensional, it could be one-dimensional, or it could be even multi-dimensional beyond 3, 4, and 5 as well. So for very complex problem. So for this given problem, what we will do is we will first find out what is the least possible subproblem, right? So if I consider the least possible subproblem for this, what it could be? So when I say the least possible subproblem, it could be just a tree with one node. Fine, it's the least possible one. If I have a tree with only one node, then it is always optimal binary search tree, right? So this will be one sub problem, this will be one sub problem, and this will be one sub problem. So once I have a solution for one single node, then I can find solution to a slightly larger sub problem. It means that now I will move to the a sub problem of two nodes, 10, 11. Then I will move another sub problem of size 11 and 12. I mean problem containing size 2 and two nodes 11 and 12. So that's how I keep on building. Then once I compute solutions for this 10, 11 and 11, 12, what I do, I now find out a solution to a further larger problem, which is a problem with size 3 nodes. Fine. And once I get this to this size of 3, I am done with the problem because I have reached to my original problem size. So that should be the approach. Fine. So what we will do is we will first find out what is the cost if I only have one single node, right? Then what we'll do, then we will find what is the cost if we only have two nodes. Then in the end, we will find what is the cost if I have three nodes. That's almost solving the same problem what we have, right? So And every time when I solve for some single problem, I always store this cost somewhere in the data structure. Now what we will do here, we will just stick to a simple table like data structure. So what we will do is we'll create a table. Now in this table, for example, here I have 3 node. So I'll take 3 node problem. So 3 into 3. Okay. Let me make it a 3 into 3 node problem. Fine. So this would be 3 into 3. I think this is not what I want. Take I'll take 4 by 4 because one column and one row I'll use it to note down index. So what I'll do is I'll store index here 0, 1, 2. It means 0 node, first node, and second node. I mean first, second, third, 0 indexed. So I'll make here 0, 1, and 2. Quickly let me make it everything centered. Okay. So this is a table where we start storing the results of solving sub problems. Okay. So when I have a small sub problem of size 1, when I have small sub problem of size 1, which means that I only have one node. And here if I consider problem size, let us denote a problem size as let us call this as something called as cost matrix. What we'll do is we'll call it as cost. So when I say cost of 0 0, if I say cost of 0 0 means starting from the index 0 ending at index 0. What is that sub problem size? Starting at 0 ending at 0, which means that it is a problem for a sub problem which starts at index 0 ends at 0, means it is node 1. When I have only one node, the cost of that is nothing but what is the cost of that? If I have only one node, this cost would be just the frequency. If I only have one node, for example, I only have one node. What I'm saying is I only have one node whose value is 10. So what will be the cost of that? The level at which this node is multiplied by its frequency. What is the cost? Only 2. So the cost here would be 2. Likewise, if I come to this location, how do I refer this location? This location I refer as cost of 1 comma 1 or cost of 1 comma 1 from 1 to 1. So if I say 1 to 1 means sub problem which starts at index 1 ends at index 1. How many nodes I have in that index range? Only one, which means the cost of tree which only consists of one node and that is 11. What would be the cost of that? The frequency. So the here the cost would be 1 for this. Likewise, what would be cost for node with 2 and 2? It would be 6. Fine. I hope you understood to this point. Okay. So I have solved for one size 1 sub problem where I only have one node. Now what I need to do is I need to find solution for sub problem of size 2. Now if I want to find out sub problem of size 2, I have two options. Fine. So how many such problems I have? So starting at index 0 ending at 0 1, or starting at index 1 and ending at index 2. So we have two problems. And what are those cells? These are the cells which represent that. For example, starting at index 0, ending at index 1. So it is cost of 0 comma 1. Let us call it as cost of 0 comma 1. So I need to find out solution for this problem cost here, and I need to find what is the cost for this location. If I say this location, what it is? Cost of 1 comma 2. So cost of 1 comma 2 means starting at index 1, ending at index 2, which means this subproblem of size 2. And finally, we have a cost for starting at 0, ending at 2. That gives the cost of entire binary search tree. So now, here I need to find values for this and 2. Remember, let us look at how we can solve for that. Now let me highlight this cell for which we will be computing that. For example, this is a cell for which I want to find out a value. What is this subproblem? This subproblem is of 10 and 11. This is the subproblem for which I am working on currently. This one. This is a problem for which I am working. So how many nodes I have? 2 nodes. So when I have a 2 nodes, remember here I have multiple possibilities, right? Let me connect this with this. So when I have a 2 nodes, what could be the cost? I need to put here the minimum cost for sub problem 0 1, means starting at 0 and ending at 1. So here how many trees I have? One could be 10 here. If I have okay, if I have 11 here, I'll have 10. How many possibilities of binary search tree I have? This is one, and it could be one more. It could be one more combination wherein I'll have 10 and I'll have 11 as child of this. So now when I consider these two nodes, these two substructures, I want to find out a minimum cost here. Okay. So what's the cost of this? What's the cost of this tree? So if you want the cost of this tree, what we do here is the level, the node. For example, I am solving for node 11. Let me put it in bracket. For 11, what we have, the frequency of 11 multiplied by the frequency multiplied by the level at which the node is, plus I have another node which is 10. So how do I get the cost of that node? The frequency of it multiplied by the level at which it is there. So what's the cost here? 4 plus 1, 5. So here, if I do the same arithmetic for this possibility, so here I have 10 and frequency of 10 is 2, 2 into 1, and here I have 11, the frequency of 11 is 1 multiplied by 2. What it is? 2 ones are 2 ones are, the frequency is 4. So which is minimum? This tree or this tree? If you look at the total cost we have computed, this is far minimum. It's minimum than this combination, right? So what I'll do is I'll note down this 4 here. This is the minimum. I'll note down the 4 minimum here, and whenever I store this 4 here, what I do is, in addition to that, I also store what was the root when cost was minimum, which node was used to arrive at this minimum cost 4. So in order to get this 4, I had to make node 10 as a root. What is this node 10? This node 10 is 0th index node. Let me just write 0 here. So let me just store that value, the cost slash the root because of which I got this 4 as the list cost. Are you getting this? Okay. So given this understanding, Let us try to understand why this is giving me least value, right? Why it is giving me a lesser value. Now, if you want to find why it is giving less value, let us understand this breakdown of this cost. See, now for this node, here, okay, let me retain that as it is. Let me write here. So when I'm working on this two node structure, remember, when I have kept 10 at the bottom, when I kept the 10 at the bottom here, let me write frequency as 2 and its frequency as 1. Okay. So as you all know that 11 will be read one time. So 11 will require one memory access, and 10 is being read twice. So 10 will require two more uh, two memory operations. So in overall 10 will, in order to, you are saying 10 will be read twice. So to read just 10 from its memory location, I need to do two memory operations, and for 11 I need to do one operations. But if you look at 10 here, 10 is at level 2, and every time I want to read 10, I need to read 11, and only then I can read 10. So that's why if the frequency of this node is higher, if the frequency of this node at bottom of the tree, if they are higher, it would unnecessarily make all these reads with what I want to say is, if I have leaf nodes at bottom of the tree with higher frequencies, they will unnecessarily increase more memory read operations. But if you consider the same for this, if you consider same for this, here you can intuitively understand. So here I have 11 whose frequency is 1, and it being at the bottom of the trees, it would obviously require more memory access because it has to traverse from root to leaf. and and if the frequency of 11 is high, every time you need 11, you need to always come from root to this node. So more these node roads and more depth this is at in the BST, more will be the more read operations. So which gives me an optimal binary search tree for this two node combination is a tree organized in a such a way wherein the nodes with higher frequency are at bottom of that. So if I want to minimize this, I need to keep trees with minimal frequency at the bottom. So if why you keep tree nodes with minimal frequency, because lesser you go to the depth of tree, lesser the memory read operations, right? Are you getting this? Now before I proceed further, let me just see your understanding. Let me know, have you understood whatever we have discussed till this point? Because more we go ahead, the problem becomes larger and larger and more complex and complex. So I'm waiting for your responses. Have you understood till this point? Okay. Okay. So, okay, coming back to this. So I hope you understood this. Fine. Now, if I want to solve this for next combination of nodes, so that two problems means I'm solving it for this node. Size at 1 and ending at 0. So this is two problem, right? So here, what are the two nodes I have? 11 and 12. So once again, I have two combinations. 11, I think this should be 12. If it is 12 here, I'll get 11 here. And if I have 11 here, then I'll get 12 here. So the cost, what would be the cost of this? What would be the cost of this? So see, we have multiplied it by level. I can also put alternate logic. So to read 12, I need one memory access to read 12, right? And how many times I read 12 here? 6 times. Yes, plus to read 11, I need two memory reads, one for 12 and one for 11. And likewise, how many times I read 11? One time. So 11 requires two memory read operations. So what's the cost? What's the cost here? 6 plus 2, 8. Now, you can multiply with 11, that's also one. The second one, I'm actually doing that. So 11, in order to read 11, I need one memory because it's a root node. So I need one memory access. Likewise, how many times I read 11? One time. So total memory reads for node 11 are 1 plus 12. To read 12, I need two memory reads, one to root, to the right of that one more memory read. So two memory reads for reading element 12. And likewise, how many times I need read 12? 6 times. So 6 to the 12. So 12 operations I need for this. It would be 13. Which is minimum? Which is minimum? So should I go for this cost 3 or should I go for this cost? This is minimum one. So what I'll do is I'll write 8 as the cost, and in order to come to that cost 8, what was the root node? What I wanted to make a root node. So what is a root node? If I consider 1 to 2, what I made a root node 2. So this 2 is an index which was made root node, and by virtue of that you have obtained the cost 8 as a minimum one. Fine. Okay, so this was for this node with two subnodes. Now what we do is, I think, am I correct? So this is one. What if I do go by earlier formula? What it is? I said 12. If I go by that formula, so 12 means frequency of 12 multiplied by level plus node 11. For node 11 means frequency of that 1 multiplied by that level. So 612. You will also get same operation here. Likewise, you will also get the same operation here as well. Okay. So this is 40 and 82. Now we are done with these two sub problems. Now we will increase the sub problem size. So we are done with the sub problem size 2. Now what is remaining is sub problem of size 3. Now here arises the, so now you can see the more complexity increasing. So we already have this size computed for this. Now the sub problem size is 3. So for what location we are calculating? This final location. So now when we want to try this, I have to find out something which is now, which will include 3 nodes. So 3 nodes means multiple combinations. Okay, so what I need to decide, remember I have 3 nodes 10, 11 and 12. I need to choose one in that. I need to make one of this as a root so that I will get minimum cost. So what I need to find out, if I make 10, what is the minimum cost? If I make 11 as a root, what is the minimum cost? And if I make 12 as a root, what is the minimum cost? So in order to do that, what I do is This is what I'll be doing. That forget about the tree. What I'll do is, see, if I have 1, 2, 3, right? If I have 3 nodes, I could have 10 here, or 10 could be anywhere in that. This could be anywhere. So whenever I compute cost, what is that which every time comes into picture? So every time if I have a BST of 3 node, I have to always include the cost of memory read operations. So whatever node which has, it has to be read, it has to be read, and it has to be read. So what I can do is I can always do this combination plus of frequency 2 plus 1 plus 6, because whatever node may be, wherever 10, 11, 12, or wherever it is, just to read this 12, just to access the value in this node, I need one memory read. Likewise, I'll be reading this. Maybe if it is 12, I'll be reading it 6 times. If I read 11, wherever 11 is there in this tree, I need to read it 1 time. So one memory read I need to do it. And wherever 10 may be in this, wherever 10 may be in this, in order to read the value of that, I'm reading it twice. I have to read it twice because frequency is 2. So the cost will be, this will be obviously the part of this. Now what I need to do is plus, I need to minimize the operations which I'll be requiring for this. So every time these many number of memory reads you have to do, means you have to do. Now plus whatever this additional memory access you do, because some node was here, and if it has to be read 6 times, whatever the value here you have, in order to get this value you need to do this extra memory read in order to come to this. So I need to minimize this extra read operations. So this extra read operations can be we have to choose that minimum operations. So here we have two cases, or rather than saying two, we have three. What I need to do is, if I make if I make 10 as a root, if I make a 10 as a root, then I need to find out optimal among these two. So if I make a 10 as a root, overall how many memory read operations I'll be having? So 10 itself, so how many extra operations I need? That's the count I am finding that. So remember, you need not further solve this small sub problem. This is what we already solved. This for a 2 node problem. See, if I make 10 as a root, what are remaining nodes? If I make a 10 as a root here, the remaining nodes is 11 and 12. What is the optimal number of cost for that 11 and 12? 11 and 12, we have already computed this. For 11 and 12, for this sub problem, which we have already solved this. So if I make 11, as a root node, I need to find what is the optimal node for this 10 and 12, which I have already solved here, 10 and 12. What if that single sub problem size you have? So if I make 10 as a root, I get a sub problem of size 2, which has to be optimally solved. If I make 12 as a root, if I make a 12 as a root, then I'll have 10 and 11 as a sub problem which has to be organized. And if I have 11 as a root, then I have two sub problems created, each of size 1, which we have already solved here and this value. So I need to find the minimum ones. So when you solve for a minimum ones, these memory operations are always required. The 2 plus 1 plus 6. Plus what you need to do is you need to find out the minimum read operations. You have to find here the minimum read operations which uh, which are fine for this the current combination of tree. So you have three values here which you want to choose minimum among that. Let me just enlarge it and find out. So 2 plus 1 plus minimum. So the first is if I make 10 as a root, if I make a 10 as a root, uh, how many, what value, if I have a 10 as a root, then what is the cost of that? See, 10 is root. So if I make 10 here as node, then I have to arrange 11 and 12 in such a way that the cost is minimum, which I already know, which is 8 by making second node as a 2. Then what it is saying that I have to make here as 12 and I need to make this as 11. If I make root 10 node 10 as a root. So what is the frequency of 10? Twice. So if I decide to make 10 as a root, if I decide to make 10 as a root, the cost of this two, what is the cost of these two nodes? Let me, so the cost of this subtree, which is starting at this cost is 8, minimum 8. So I have made 10 as a root. If I make 10 as a root and this optimal, this sub problem which I've already solved optimal way, what will be the total cost? How many extra operations you will read? Can you guess that answer? How many extra operations I need? 11 and 12 are this. This entire subtree requires cost as 8. So how many sub operations it will require? So this is the additional memory read operations if I make 10. So when I say 8, it means 8 memory reads here. 8 memory reads occur here. For every memory read operation, I will need to read this 10 once. So 8. So 8 read operations here. So when I say here 8 read operations, 8 into, so 8 read operations, this is what you get, that if you make 10 as a read operation, so basic cost plus 8 read operations if you make 10. If you make 12 as a node, if you make 12 as a root, what's the sub problem I have? The sub problem I'll be having is this one. So 10 and 11. So 10 and 11, I already have a least cost 4. So if I have this here as 4, if I have this here as a 4, then I already have. So 12 is 1. I need to find optimal way of storing the subnodes. Subnodes containing problem 10 and 11, which I've already computed 10 and 11. If I've already computed 10 and 11, I need to make 0th node as a root node. So 0th node means 10. And if I keep 10 here, 11 has to be right of that. So this will require 4 read operations. So if 12 is a root, then the minimum operations, see, I need to, what I said, all the below one need to have least number of frequencies, because more number of frequencies or more read operations you do at the depth of the tree, it increases more unnecessary reads at the top of the tree. So here The minimum read operations here is 4. Okay, so this is what sub problem 10 and 12. But if I make sub problem as, if I make 11 as a root node, then it will create two nodes, 10 and 12. 10 and 12 can't be under this one. So that would now create, two sub problems underlying that. So what is that? So the every time you read this one plus every time you read this, that many number of times the 11 will be read extra times. So 10 means 0 and 0, 0 and 0. So 2 plus 12, 6. So 8 times. You need 8 times. So what is minimum of this? So the total memory read is 2 to read 10, one memory read operation to read 11, plus 6 read operations to read 12 6 times, plus minimum of this is 8. So what's the overall cost? 2 plus 1, minimum is 4, not 8. This is the minimum one. So if you do this, 6 plus 4, 10, it is 13. And why is 13? It is 13 because you have made um, 4. 4 as you took 4. So when was that 4 possible? 4 was possible when you have chosen 12 as a root node. This was when you had to choose 10 as a root node. This was when you had to use 12 as a root node. This was the cause when you had to choose 11 as a root node. So, you will make here 13, and when choosing 12 means 2, index at index 2 we have 12, that's why I written 2. So that would give me the minimum cost 13. So overall we get low total cost of BST is 13. Now if I want to construct tree back, I started this 2. It means that I made 2 as a root. So now when you go to 2 as a root, you will you can just get this value from this itself. So when you start constructing tree back, either you can trace values from this side or you can start with 2 here. So start with 4 2. uh, you can start with two node problem, then here you will get two node problem, you will make node, and both of this, when you go to the top here, you can properly choose the root node of that. So when you are here, they're all individual nodes, so you can construct tree by just looking from leaf to top. Look at leaf nodes, then when you have two nodes, you create which is this, and which among this will be root will be decided at the top level. Okay, so what is, have you understood this, what we have worked out here, or you felt this is too complex? Let me know what it is, or else I'll explain again.
Can you just respond? Have you understood this? Why it is 13? Why I took minimum? So this minimum would also work for this, but we didn't go there. The tree was smaller, but that's why we did it. But there too the same minimum operation works. Let me know if you have understood or not. If not, I'll try to explain this again from this tree part. Can you respond?
Or what we can do is we can take one more problem. Let's say we take another problem here. Let me make a space for another problem here. So if I take another problem, uh, another problem nodes are, let us take it as 10, 12, let me take some solid example, 10, 12, 16, 21. And their respective frequencies are 4. So what if I solve for this problem? Okay, so can you just let me know, like, have you understood this or not, or shall we solve another problem where you can understand it? At least let me know, have you understood this? Why I have uh, taken this minimum?
Yes or no? Like whatever it is, if it is no, let me know because Have you understood? Can you explain one more example? Okay. 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 So, okay, let us solve another problem then. Uh, yeah. So what we'll do is we will use this problem. So whatever we have, we'll just remove it. We'll also remove that. So this is a problem for which we'll try. So I need to add one more column to it. Insert. So we have 0, 1, 2, and 1, 2, and 3. Okay, so this is the matrix which we have initialized. So now if we when we want to solve for optimal binary search tree for this node 10, 12, 16, 21 with the frequencies as 4, 2, I mean the frequency of 16 is 6 and the frequency of 21 is 3. This is what I want to solve for. So initially, what are the minimum sub problems? 1, 1, 1, 1. So as I said, we will always start with the minimum possible sub problem. The minimum sub problem means a node with a tree with only one node. So 0, 0 means if I only have a node at 0th index 10, if I only have a node at 10th index, provided I only have node 10 and given frequency 4, how many times that's being read? 4 times. So the memory read operations will be 4. So for 1, 1, it would be 2, which means node 12. And for node at index location 2 and 2, a sub problem starting at 2 ending at 2, 2 comma 2 means 16. How many times it's being accessed? 6. So 6 read operations. And 3, this would be total read operation will be 3. We have solved it for 1, 1, 1. Now we have sub problems of size 2, which is this is sub problem of size 2, second sub problem of size 2, third sub problem of size 2. So what I'm considering is if I have a sub problem which contains node 1, node 0 and node 1, which is 10 and 12, what should be the optimal binary structure? So how do we do that? So when I say optimal binary structure, here you will understand it better. So two node problem. What we are solving for? When I only have two nodes, what it is? 10 and 12, which means I am solving it for cost of cost of 0 comma 1 means 0 comma 1. For this cell I am solving it for. Okay, so if I solve it for this, I have two nodes 12 and 12. If I have two nodes 10 and 12, the total memory read operations, what are total memory read operations? To read 10, and how many times I'm reading 10? 4 times. So 4 read operations for just reading 10 plus 12. How many times 12 I am reading? 2 times. So 2 read operations just to read 12 plus the additional operations which are needed. What are that? The additional read operations which are needed if either 2 or 10 are at different levels in that tree. Okay, So here when I say 10 and 12, now I think here you will understand it better if I show you. So this is 1, this is 1, and okay, and let me create it. It won't take much time, just I have this. So when I have 10 and 12, let's suppose here it is 10, here it is 12, and if I make it as 12, if I make here is 10, obviously this 10 would go to right of this, and this would go to, so we have this two combination. What I'm doing is, no, see, no matter what I choose this, if I choose this structure or if I want to choose this structure, no matter what I do, I need to read 10 and I need to read 12. I need to read 12 here, I need to read 10 here. But so 4 times I read 10, so the 10 operations, 2 times I read 12, so 2. Here too, if I do this, 2 times I need to read 12, so 2 here. Here too I need 10, 4 times I need to 10. So minimum, so for this structure, let me first highlight it for this structure. If I consider this structure, if I consider this structure, and if I consider this structure, okay, initially I am considering for this structure. If I consider this structure, how many additional read operations I need to do? Basic 4 plus 2 I need to do it. Plus, since 12 is at leaf node and frequency of 12 is 2, I need to do 2 additional read operations just for reading 10. So what is this 10 here? Sub problem of size 10. So 2 is 1. So I'll make this 2 as red color. So min of 2, or if I make 10 as a, if I make, if I make 10 as a, I think this color, okay. Okay, if I consider this tree node, if I consider this node, how many additional read operations I need to do apart from this basic 4 plus 2? 10 is here, 10 is being read 4 times, and every time you read 10, you need to read this one extra operation here. So how many extra operations I need just to read 10, because 10 is at lower one? Here you need, how many times you need? 4 times you are reading 10. 4 times you are reading 10. So 4 times means 4 operations here. 4 additional extra operations. Fine. So total read operations will be 4 plus 2 plus what is min of this? 2. So if this min of this is 2, means total is 8. That's why you're getting 8 for this. So here what you will do is you will write 8 and you will choose root. What was the root when you had two sub problems, 0 and 1? You made 0 as 0th node as a root node. That's why you got 8 here. So this is what I did in last 3 by 3 root node format, right? Are you getting what I'm doing that? So 4, this 4 for reading, just to read 10, just to read 12, and here I need to find min of both. As you see, if I bring 12 to the bottom of this, 12 is being 2 times, so 2 times this additional 10 has to be read. If I bring 10 here, 10 is being read more number of times. So more number of times this is being read, more the additional read operations till the root of the tree. So I need to find minimum among these two. And this minimum which you have already solved here for 0 and 0. This two and this two. Are you getting this? Let me know have you understood this step. Now you should understand this 2 and 4. Let me know if you have understood this. If you have understood this, then I think it is far easier to understand our previous problem, the complexity thing. Okay, tell me now. I think most of you were in confusion. Let me know if that confusion has been cleared or not. Now it should be clear if when I solve it for this problem. Yeah. Okay. So Shubham and Rahul, I think Rahul Patil, I think now you should be able to understand what exactly is that. Okay. Yes. Yeah. So this is additional read operations what you need. Likewise, if I do it for next sub problem, what is next sub problem? 12 and 16. So let us do it for 12 and 16. So if it is 12 and if it is 16, I am working it for 1 comma 2. So it is 1 comma 2. I am working for this cell location, this yellow color location. Okay, so if I do this, here you have two possibilities. Once again, you can make, if you make 12 as, here you will get 16, right? And you have two sub nodes. If you make 16 here, and if you make 16 and what will I have here? 12. So now what will the cost here? So to read 12 I am reading twice. So two memory operations are required. 16 I am reading 6 times. So 16 are basically required for this. But here I need to find the minimum ones. So if I make 12 as a root and if I bring 16 as this, since 16 is being reading 6 times, you need to read 12 unnecessarily 6 times. So what you have here? 6. So 6 minimum read operations you need because 6 extra. 16 is it root node. So in addition to its reading 16, you need to read 6 times the 12 above it. So 6. If you make 12 as a root, if you make 16 as a root, if you make 16 as a root, how many times 12 is being read? Twice. So twice extra operation you need to do. So 2. So what is minimum among this? This 2. So what is the total cost? Once again it is 8. So you will get 8 here. And why did you get 8? From 1 and 2, what you made root? You made root as 16, which is at index 2. Likewise, when I come to 2, 3, when I come to 2 and 3, this problem 2 and 3, I'll have 16 and here I'll have 21. So the cost of, I'm working for sub problem 2, 3. So 16 I need to read 6 times. So minimum 6 read operations I need to do for this 16. I cannot escape from this. 21 I am reading 3 times. So 3 times I have to access. I have to read 20 times. But what can I control is, this is what I can control. So once again I'll write it here as 16. If I write 16 here, 21 will be to the right. If I make 21 root, these are the only choice I have here. Either I can make 21 as a root or I can make 16 as a root. If I make here I have 16. Here I'll make it as 16. So now when I make 16, you need to do, if I make 16 as a root, if I make 16 as a root, then, or I can call alternatively I can read as, if I make 20, if I bring 21 to the leaf node, 21 is being read 3 times. So 3 times extra you are reading 16 3 times just because 21 is leaf node. So the frequency, so you can see the frequency of reading 21 here. Then
16. 16 means 16 you are reading 6 times, which is at leaf node. So every time you need 16 6 times, you are reading 6 additional. So for this 16, minimum 6 operations, it will always result into 6 additional operations if 16 is leaf node. So 6 additional. So what is minimum here? 3. So if I make 3, 4 plus 2, 6, it is 9. Here it would be 9. And 9 when I have made 16 as a root. 16 means 0, 1, 2. 2. Okay. So this is what you have solved second level. Now let us solve it for this complex, little complex the problem will arise now. Okay. So now when I solve it for sub problem starting at index 0 and ending at 2, what we have? We have two further nodes. Let me solve it for one case and that should be clear for that. Now what I have is I am solving it for 0 to 2 sub problem of size 3. So I'll solve sub problem of size 3 for this. Then I have sub problem for this. First sub problem and this second sub problem. So first sub problem means 10, 12 and 16. 10, 12 and 16. So if I do it for 10, 10 is there, I have to read it 4 times. The minimum memory read operations will be 4. 12 I need to read twice, minimum will be there. 16 I need to read 6 times, this is 6 times. Plus now the min increases more. Now see, earlier I had only 2 nodes, so you had only 2 choices, either to make first node as a root or second node as a root. So now here you need to have 3 minimum operation. If you make first node as a root, second node as a root, and third row as a root, so you have 3 min operations. So let us solve that. If I make first node as a root, what it is the first node? If I from this 10, 10, 11 and 10, 12 and 16, if I make first node as a root, if I make a first node as a root, then here instead of doing this, let me take one more simple. Let me explain. I think okay. So it will okay. If I make 10 as a root node, then I have here it will contain a tree. It will contain a tree which will contain 12 and 16. Okay. Now your problem is to also store this 12 and 16 optimally. But remember this 12 and 16, for example, this 12 and 16 means 0, 1 to 2. 1 to 2, this 12 and 16, this you have already solved. You have what is the optimal binary cost and what has to be made root. So this is already written here. Are you getting that? This we already solved this. So for 10 you will get 1. If you make 12 as a root node, if you make 12 as a root node, the total sub problem, the subtrace which you will find is 2 ones. This is 1 and this is 1. You will have these 2 subnodes. Okay. And you will have one more combination. You have one more combination in which you will be making 16 as a root node Then you need to find out an optimal tree with subproblem 10 and 12. With subproblem 10 and 12, which you have already solved, subproblem 10 and 12. It will be minimum cost will be 8 and this, right? So here, let me make this in some different color, then you will understand it far more clearly. Fine. So these are three combinations. So I need to do how many extra operations I need if I make 10 as a root node. And if I make this 12 and 6, you know that 12 and 6 will totally need 8 read operations, right? So this total number of additional for every 8 operations you need to read 12 and 16, you need to do one extra read to need node 10. Only after reading this node 10 you can go to this tree. And in this tree of these two nodes, the optimally you can search is 8 memory operations you need that you already computed. So the total number of additional will be, so 8 you will need for this one. So 8 operations which you need for this. So for each of these 8 operations you need to do this one additional operation of reading 10, which is 1. So total will be how many minimum operations? 8. 8 operations you will need if you make 10, right? Likewise, if you do it for 12, what is the subnode here I have? If I make 12, here it is 10 and here it will be 16. So if I only have 10 here, if I have 10, what is the memory read operations you are doing? 410 memory read operations. And if it is 16, how many memory read operations? Only 116 you have? 6 operations. 16 means this 16 I am talking about. This 6 operations. So how many extra memory reads? So every time you read is 4, you need to read 12 and come. So 12 is read 4 additional times here. And every time you do 6 times here, 12 is 1. So total read operation will be 4 plus 6. So here it is 4 plus 6. This will, I'll put it in green color. Plus minimum, if you make 16 as a lower one, if you make 16, what is the total minimum operations, optimal binary operations if I have a tree with node 10 and 12? Tree with node 10 and 12, tree with node 10 and 12 means 8, right? So this you will make 8 operations here. So if you need 8 operations here, if you make 8 operations read here and I make 16 as a root node, how many minimum operations additional I need here? 8. So this I'll make this 8. So you have two 8s, you can randomly choose one. Let us do one thing, we will choose this 8. So you can choose to make any of this as 8 here. So what the total cost? 6 plus 8. 6 plus 8, 14. So it will be 14 for 0 to 2. And 14 was there because you have chosen 8. 8 means the 16. 16 was made when you have considered this 8. 16 was root node. 16 was the root node. So 16 means 0, 1, 2. The 2 becomes root node. So now you have to solve it for this. If you solve it for this, what will be here? Now it would be 12, 16 and 21. So it's a problem of 1 to 3. If it is 1 to 3, what is the minimum operations I require here? The minimum for 12 is 2. 16 I am reading 6 times. 21 I am reading for 3 times. Plus I need to do minimum. Now tell me here. So I have these two more options. If I make 12 If I make 12, what I have here 16 and 21. 16 and 21. If I make 16 as a root, if I make 16 as a root, here I will be having 12 and here I will be having 21. And in the end, here I'll have 21. If I make 21, here I'll have what I'll have here 12 and 16. Here I'll have 12 and 16. So now tell me which is minimum here. If I make 16, 21, 16 and 21 means 1, 0, 1, 2, 3. Where is 2, 3? 2, 3 means 2 and 3. Sub problem of size 2 and 3. What is sub problem of size 2 and 3? 16, 21. So 9. And if I make 16, 12 and 21. Where is 12? Where is 12? 12 and 21. So either of this 6, only just 12, only just 21 to the left. 6 plus 3, 6 for 12, 3 for 21. This is the frequency I'm saying. So if I make 21, 12 and 6. So sub problem containing 12. 12 means index 1, 16 means index 2. 1, 2. 1, 2 is 8. What is minimum among this? This is 8. It's already 8 here. So 12 and 16. 12 and 16. So size starting from 1 ending at 2. It is 8. So what is minimum? It is once again minimum. So what you will get here. So what is minimum now? Just let me know if somewhere if I might have I'm not sure like earlier. So what it is 2 plus 6. What is 2 plus 6? It is 2 plus. So this would be an operation. So 2 plus 6, 8, 16. So it should be 19, I guess. So it will be 19. And it was because when I made this as a root, 21 as a root. So 3. I think this we have not computed correctly. The cost for 1, 2. Yeah. I think the cost for that, I think something we have gone wrong. Cost is 10 for 1, 2 sub problem. 1, 2. Where is 1, 2? Yes, it should be. See, during this explanation, I might have gone wrong. I hope you can uh, you are keeping track of that. Yes, I think the 1 and 2. This would be 1, 2. It will be 10. Yes, it's not 8. I think we missed. It would be 10. Cost of that would be 10. And I think this two, I think we have miscalculated. It should not be 9. 2, 3. It should be, I think it should be 12. Yes. If it is 12, then if it is 12, then we will get here it as 20. It will be not 14 as well. It should be 20. See, I think I just forgot doing this sums. Maybe I missed it. So I was in explaining you this concept. I hope you are understanding that. Okay. See, my sole purpose of this additional expression was to explain you this. Why I am taking this min. This was maybe I might have missed something here, so that might have affected the computations. Okay.
So I think this don't work on this values. This might be wrongly computed. Don't go for this one. Since I changed these values, this could be different values. Okay. So I think we have exceeded too much of time. Like, just see, my intention was to explain you this concept. What is this mean, and how these values are being computed based on sub problem. Because if we have this understanding, only then we can write a program. Else writing program would have been very tough unless we figure out a logic for structuring this properly. Writing program to solve this would be very tough. So now in our next lecture, we'll try to. So what I want is, I want you to solve this problem. I want you to solve this problem and find out what value you will get here. And based on this logic, we will write a Python program. So that should be far more clear. Okay. So just let me know, have you understood this? Have you understood the approach? Maybe we might have gone wrong in computing for second example, but have you understood the approach? Specifically, I want you to understand this min, the min one, what I'm doing here. Because if we don't understand that, implementing it in program will be very difficult. That our earlier method of doing by level multiplying, that is good intuitively for solving manually, but I cannot use that approach for implementing it in a program. I hope you are getting that. So you can once again solve it for all these values with proper minimum nodes. I think for 2 it 10 10 8 10. Yeah, it will be only 10. I think this is the only thing we have gone wrong. So now you can work on computing these two values. This will be 10. I think we just missed one addition there. So a final question. Have you understood this? Okay. So if you can compute these two cell values, these two cell values and these two cell values, you will get an answer. So we will revisit this problem. What I'll do is, I'll stop at this point. I'll stop at this point. Tomorrow we'll continue at exact same point. I think tomorrow means on Friday. And then we will write a Python program. You will be amazed to see how easy it is to write a Python program given we have a proper logic. We have to only work on this table. That's it. Just two nested for loops, you will get an answer for this. But approach here, what we saw, it took more time. Okay. We'll continue from the same step on Friday and we'll write a Python program which will give me the optimal binary tree cost for this. I hope this lecture was helpful. Maybe it might took long time, but this was needed. Okay. So that's it for this lecture. If you have any further questions, or if you want to try it for this for further one, we can discuss this in a Telegram group. So that's it for this. I think I took more time. I'll just put messages in there to give you some additional time for you. So that's it for this lecture. Let's meet on Friday then.